get this started. Here we go. Buffers.
Two.
We have talked some of the things about buffers we have talked about either in last unit or in this unit, but we're gonna go straight into it. Don't hate me because I'm a little buffer. Okay, so a buffered solution, I think I mentioned this before, is a solution that resists change to pH. Okay, so in order for a buffered solution to occur, we have a common ion involved. And usually the common ion would be, from a salt that's been dissolved, so that in equilibrium for the acid or the base, it will prohibit the shift, so that it will prohibit more ionization of the H plus or the OH if it's a base. So it just will resist or stabilize pH changes. And we have an example, I think, that we will see like what it is in pure water versus what it is in a buffered solution to see that it's going to be very, very very, very close, small difference between the two. Okay, so a very practical example of a human or of a buffered solution is our blood in humans, because our blood can absorb acids and bases that are produced by our biological reactions as our body is processing things without changing pH. So it has dissolved substances in our blood that help prohibit any changes to pH in our blood. And this is important because our cells can only survive within a very narrow pH range. So if you have strong changes or very large differences in pH, that could potentially really be harmful to your body. So a buffered solution could be a weak acid and its salt. So like, for example, hydrofluoric acid, HF, and NaF. So the common ion there is the fluoride ion, the conjugate base, okay? Or a weak base in its salt. So like ammonia is NH3, and then ammonium chloride, the NH4 plus 1 ion from the ammonium chloride would be the conjugate acid in that situation that would also be present. So the appropriate components will allow for a solution to be buffered at virtually any pH, whether it's an acid or a basic solution. So when we are solving buffered solution calculations, we have to consider a few things. First of all, we need to see what the common ions are, what is being given to us that's important from that salt. So remember, get rid of spectator ions and that kind of stuff. And then we will then just see how this applies to resist the change of the pH. So just remember that these are merely solutions that contain weak acids or bases. So the actual procedure to solve them is going to be similar to what we have been doing since 8.3, okay, section 8.3, where we will have our Ka expressions, we'll have our equilibrium expressions, and all that kind of stuff. But the salt concentration will give you, for initial and your ice chart, will give you a value instead of 0. Okay. So the first one I have is a lot simpler than the next one I have. So a buffered solution contains 0.5 molar acetic acid, Ka listed there, and 0.5 molar sodium acetate. So we want to calculate the pH of this buffered solution. Okay, so this is very similar to what we've been doing, but it's just a nice brain warm up. Okay, so from the sodium acetate, the important part is the acetate ion, the C2H3O2. Okay, so if we think about like everything that's in the beaker, right, like major species is what you could say. Sometimes you might have to think about this yourself, so it is good practice to do, but to save time, sometimes I don't do it. So we've got our acid, I'm just going to say HA, for this acid right here. Okay, that's what I'm calling HA. Then we have water, because they are aqueous solution. Then we have the sodium ion, and then the acetate ion. So I'm again just going to use A minus for that acetate part. And that's it. So we are having this solution of the sodium acetate, and we're going to pour some acid into it. And so we want to know, what will the pH be after it all works together? Okay. So like I said, the acetate part is the important part. The sodium is a spectator ion, so we don't have to think about that. And so since this is an acid, we can use the acid dissociation equation to plug in what we know. Let's see if I included a blank page for myself. Nope, I didn't. Here we go. Let me insert one really fast. Okay, so for the acid, right, we have our AJ breaking down into the H plus or the A minus. You could do it that way, or if you want to try to be right by the AP standards, you could have also written that the acid is put into the water to make the hydronium in the conjugate base. Either one of those is fine. Because remember, technically AP would prefer to have the hydronium than the H plus. But the math is going to be the same. So we would calculate it. The answer will be the same either way, right? So the for an initial concentration, we are given that we have 0.5 molar of our acid, and water doesn't have its concentration, so we don't include that. And then we already have 0.5 molar of our sodium acetate. So that 0.5 molar from the salt solution goes with the conjugate base, right? So this is where that common ion comes in. And then we don't know what the concentration of the hydronium ion is, which the hydronium ion is what leads to our pH answer at the end. So that's what we're going to need to solve for. Okay, is this sounding familiar from last week? Hopefully. Okay, so our changes, we always add to the zero side. So at equilibrium, we got 0.5 minus A for HA. For the hydronium, it's A, and then for the conjugate base, it's 0.5 plus A. Okay, and then we haven't done this in a while, but if you're still struggling with this part, remember it's always products over reactants. So the concentrations of these two over the concentration of the acid is what we'll plug in to solve for the value that we need. And so when we plug it in, we are able to make assumptions because we know that since it is a weak acid, not very much of it will dissociate. So we can assume that A will be so small that it won't really change when we subtract or add it. So when we plug in, the Ka value was given 1.8 times 10 to the negative 5 is equal to, and we're going to just say A for that times 0.5 for the conjugate base over 0.5 for the acid. All right, so then the A is equal to whatever the Ka value was, which is really nice. And so that would be your hydronium concentration. So then to find pH, we just take the negative log of that. which is 4.74. Okay, so this math that we've just done is very similar to other stuff we've done. How we could compare this is if we took this 4.74 and compared it to what if the acetic acid was just in pure water, and see and do all the math and have this is 0 for this spot right here, solve out what the H plus is, and then solve for pH that way. And we would see, if you did that, that there wouldn't be very much of a difference between the two. Because that's what a buffer does, is it resists change so that the pH will stay very, very close. It might not always be the same number, but it will stay very close to what the original pH was. Okay, does that make sense so far? Okay. So then next, example 17. Okay, so in example 17, we want to calculate the pH that occurs when 0.01 moles of solid sodium hydroxide is added to 1 liter of the buffered solution that we just had. It says example 2. That may be wrong, but it's the example that we just had, so that should be changed to 16. I'm sorry. So we want to compare this pH change with the one that occurs when it's added to water. So we are going to have to do 2 situations. One when it's just with pure water, and one when it's in this buffered solution. And then to find the change that it's asking us to solve for, this pH change, we would take we would have to subtract the 2 pH values to get what that change is. Okay, so we're going to solve for 2 pHs 2 different ways, and then subtract them to see how different it is. And it's going to be a very, very small difference. Okay, so let's start with the easy way first. How about that? Does that sound good? Let's just do it when it's compared. So we're going to forget about the buffered solution for now. We're going to first solve, because we're just making our lives easier at the beginning. We're going to solve for when the sodium hydroxide is just added to water. What is the pH of that? Okay. So is sodium hydroxide a strong base? Yes, it is. Yes, it is. Which is really nice. Yes. So since it is a strong base, because it has hydroxide, right? It's a strong base because it has hydroxide. That means that we don't have to do a whole ice chart thing. We just know right away what the concentration of the hydroxide ion is. Okay? So the hydroxide ion comes directly from there because it will completely dissociate. And it has to do with this moles in 1 liter. So remember that to find the concentrations, technically this is molarity. So it would have to be the moles divided by the liters, which in this case, since it's just 1 liter, it's just 0.01 molar for that. So then we need to find the pH of the solution when it's in the water. So there's multiple ways to do that. We could solve for the pOH and then subtract from 14. We could use the KW, solve for H plus, and then take the negative log. What would you guys like to do? What would be the thing that you would do? If we have to get to pH, what would you think to do first? Take the negative log to get pOH? Okay, so let's do that. So when we take the negative log of this number, that doesn't equal pH yet. That's just going to be pOH. So when you take the negative log of that, what do you get? 2? Yes. So now for the pH, we are going to subtract from 14. Subtract. That's subtract. So that would be 12. Okay. Okay, so that, we're gonna come back to that in a second. Now, we're gonna have to do like we've done, oops, sorry. Let me add another page. We're gonna have to do like we did in earlier this unit, where we have to do like use it up with the reaction before we can solve. Okay. So now we're going to go back to adding it to the buffered solution. Okay, so we know in our buffered solution we have, these are the species that we have that are important. Okay, we've got water. We always have water. We have our acid, AHA. We have our conjugate base that's present in there, right? And then now, one additional thing we have, well, we already have two additional things. We have sodium and we have hydroxide from the sodium hydroxide, remember, because it's going to completely dissociate. So the sodium is still a spectator ion, so that's not going to have any effect. Excuse me. But the hydroxide will. So what the reaction that we're doing at the beginning, we have our buffered solution, and we are going to add sodium hydroxide to it. So we have our acid, and we're going to add the hydroxide. And when that happens, the acid will donate a proton to make water, and then the conjugate base will be left over. Okay, so this is the reaction that we're doing. So this, since it's the reaction, this is where we have to do the before and then the reaction change and the after to use up the limiting reactant. Okay, since we're dealing with 1 liter, we can just assume that everything's molarity. If you look back on the last example, it was just already given to us in molars, right? So we're just going to go ahead and plug in that if we have the 0.01 moles in 1 liter for the base, it's just going to be 0.01 or molar, sorry. And the before for the acid is what it was from the last example 16, which was 0.5. 0. Okay. And then water doesn't matter. But then in our buffered solution, we have some of the conjugate base present, right? From the sodium acetate, which it was 0.5 molar. Okay, so now the limiting reactant is pretty obvious, right? It's the hydroxide. So we subtract the 0.01 from the reactants and add it on the products. So after the reaction, when they're first mixed, then the acid is now 0.51, base is none, and then the conjugate base is 0.51. Sorry, I should have subtracted and I added. This should be 0.49. I just caught that. My bad. Okay. So then now that we have our values, next step, that was step 1, let's do the reaction. Step 2, now let's figure out how much dissociates to get the pH. Okay, so the next equation we do is for the dissociation. So it changes to be like the equation we used last time, where we have our acid, and now we're going to say that it dissociates with the water so that we can get the hydronium with the conjugate base, because the hydronium leads us to pH. Okay, so for this step then, for our ice chart, now we're going to plug in these values on the A, right? So Now we have 0.49 for the acid. Water doesn't matter. Hydronium doesn't start with anything, but for the conjugate base, we have the 0.51. And then change, subtract from the acid, add to the product side. Okay. So then here, we're going to use the same Ka value, but to save some time, I'm just going to replace from our last example how we had 0.5 over 0.5. Those numbers have changed now because we had a reaction happen. So now it's going to be the Ka value is the same, 1.8 times 10 to the negative 5 is equal to A for hydronium times 0.51 for the conjugate base over 0.49 for the acid. So then A, this time, I got to be 1.7 times 10 to the negative 5 molar. Times 10 to the negative 4. I might be wrong. Okay. Okay. Okay, so then the pH of this, we would take the negative log of our 1.7 times 10 to the negative 5, and that then is 4.76. Okay, so now with what we did at the beginning, I can't for the life of me think about why we had to do that. So I'm gonna think about that for a second. But what we're gonna do with this number, the 4.76, if we go back to the last example, what was the pH that we got there? 7.47, right? So from example 16, we got that the pH was 4.74. Okay, so the pH of the buffered solution, once everything was all mixed together, was 4.74. So what this 4.76 is showing is that when we added just a little tiny bit of strong base to the mixture, and it reacted to change what the concentrations were to make new values at equilibrium for pH values. The difference between these two is just 0.02. So this is what a buffered solution does, is that it will barely change the pH value because it's there to resist and doesn't create as big of a shift. Does that make sense? Does everybody see that? That this is the OH added one, and then this is what the original value was. So the pH change is very, very small because of that buffer. Okay, I know what I was supposed to do with that other number. Okay, I know what to do about the other one. So anybody have questions about this? Does it make sense? Hopefully. I know what I was supposed to do now. It makes sense. I figured it out. Okay. So when we found the pH of the sodium hydroxide solution in water, right? We got that the pH value is 12. Okay. What's the pH value of just water by itself? 7, right? So the pH of just water is 7. So when you're not adding it to a buffered solution, this is what I was supposed to say. I think I figured it out from my notes. So if you're not adding a strong base to a buffered solution, what's the difference in the pHs here? 5, because we have 12 minus 7 to get 5. So the difference is a lot larger when there is not a buffer present. Okay, so when you add a strong base to a non-buffered solution, just a regular water solution, the pH change will be very drastic. But when you add it to a buffered solution, that's when you get a very small change in pH, like we had that difference of 0.02. Okay, so that's what it was supposed to illustrate. So, it says to compare this to what happens. So the difference for the first one, for the buffered, was 0.2 versus the difference when it wasn't buffered was 5. So you could just say something that when it's added to a buffered solution, it's very small changes. That would be the answer. Just a few more things about how buffered solutions work to go along with our calculations we tried. So one, buffered solutions are simply solutions of weak acids or bases that contain common ions. So just remember that. So the pH calculations are exactly the same process as what we learned in 8.3. So it's just a lot of repeats there. And two, when a strong acid or base is added to a buffered solution, it is best to deal with the stoichiometry of the resulting reaction first. So you know how we do the before reaction after to use up the limiting reactant. And then with those new concentrations, consider the equilibrium calculations. So number one special concept is talking more just to relate back to example 16. And then example 17 is what it's talking about to do with number 2, how we had to use up the strong base that was added first to then figure out the process to get to pH. So how does buffering work? Well, when we have the strong base, like the sodium hydroxide ions added to a buffered solution, what it does is it will replace, we have to use up that hydroxide to replace it with the conjugate base instead. The hydroxide ions are not allowed to accumulate. So that's where we do the whole math to do the use up portion or to subtract away the hydroxide ions, like we did in example 17, using this reaction where the OH minus, the hydroxide, is representing our strong base, and then the HA represents our weak acid, and A minus is the conjugate base of those. So once it's used up, we replace it with that conjugate base, which then gives us a number for a common ion to then reduce the amount of the hydronium ion that's created when the acid does dissociate. It stops the shift from happening. So the stability of pH under these conditions can be understood if we rearrange the expression for the dissociation of the weak acid. So Ka is given just generically, and then if we rearrange that to find the H plus or the hydronium, then that ratio of acid over conjugate base concentration is important for us moving into section 8.9. Okay, and just knowing that that's how it can be rearranged is also just helpful for our calculations. So when the hydroxide ions are added, then the acid is converted to the the conjugate base form. And so that makes the ratio of acid over conjugate base decrease because we're making the denominator number larger. So that would make a smaller fraction for the ratio. But it's important to note if amounts of the acid and conjugate base originally present are very large, compared to the hydroxide added, the change in the ratio will be very small. So it's safe to assume that the ratio will remain virtually constant if the amounts are very, very large compared to how much hydroxide is added, which we had very little hydroxide added compared to the amounts in example 17. So this is just a little review where to show how the concentrations of the acid with the conjugate base relate to each other. So the shift left, when we add more hydronium ion or proton, that will increase the ratio so that we have more acid. And when we have more acid, so I'm looking at the pointing left side, then that would decrease the amount of the conjugate base. But the thing is, they increase and decrease by the same amount. So that's not going to change the actual ratio. Same thing if you add hydroxide. Yes, the base will increase and the acid will decrease, but they change by the same amount. So the ratio will stay the same. Okay, so this is just a little bit more information about how buffers work.